So one of you told me that I am on live, so I'll be proceeding from here. This is where we left yesterday in the last class, and uh, I was like, we'll spend less than 10 minutes on each PPT, right? So let's see if that is possible. So what we'll be doing now is we will just skim through the derivations because derivations are not coming anyways. Uh, we'll just look at probably the important in quotes important things. Let's just see. So previously we have seen electric field in a medium. We have seen electric field in a medium, and now we are trying to see electric field in a conducting medium. So what's the difference? In a conducting medium, you will have some free charges around. So that will affect the electric field somehow. So the change is this one. You got something here where sigma is conductivity. So fine, we are not getting into derivations. So they were like, if you go through the same procedure as before we only had this one. In a medium, we had mu and epsilon. Only this much we have. But now that we are in a conducting medium, we have uh, free charges around. So that will affect that will affect the equation. So if you try the same procedure, the variable separation method, all of this will happen. You don't have to go through the derivation. All of this is derivation. So finally, what happened is you get this. So instead of k here you have alpha. Instead of k you have alpha, and alpha is given by this. So I wonder if you would be asked to write the exact expression for alpha. And by the way, what is alpha here? Alpha is okay. And let me go a step back. We got this one, and here gamma is a complex number, and alpha is the real part, and beta is the imaginary part. If you look at the derivation, you'll understand. But this is very similar to our previous electric field, right? We got it looks similar to that, but now we are in a conducting medium, and it changes the equation. So the changed equation is this one. This is the new equation. And I told you here plus or minus shouldn't matter, but we will be taking minus. It's just sign convention, time dependence. We discussed this in the previous class. Mm, the other new thing is this one. So beta is given by this formula. So you have beta, you have alpha. I don't think they will ask you to remember this because it is looking complicated. Beta is simpler to remember, so you could remember beta. So what does this mean? It means as the wave propagates in the medium, it the amplitude keeps decreasing. So there is an exponential decay in the amplitude. So there is a term for that. Attenuates. So the wave attenuates. Basically, its amplitude decreases. So it will look like something like this. So the amplitude is exponentially decaying as it progresses, as it propagates through the conducting medium. Is there anything else? Okay, skin depth. This came in the quiz, right? So okay, so if you want to answer what is skin depth, then you'll have to know beta formula. Alpha. Yeah. Okay, there is another formula for alpha and beta. That is, for a good conductor, alpha is approximately beta, and this is approximately equal to this much. So this is simpler to remember, so you can keep this in mind. But I don't think they will ask you to remember this exact expression for alpha. You can remember the approximate value of alpha, which is approximately beta, which is approximately this much. Okay, what is skin depth? Skin depth is Hmm. Okay, skin depth is basically uh, it's like uh, let's say your wave is starting here. If it propagates through a distance of skin depth, then its amplitude will get reduced by a factor of e. So if initially if your amplitude was a, here your amplitude will be uh, a by e. So skin depth is basically the distance uh, traveled by the wave such that the amplitude gets reduced by a factor of e, something like that, 1 by e or whatever. So you get the point, right? If you substitute 1 by beta, see, if you substitute z as 1 by beta, you will get e naught e power minus 1. So your amplitude is multiplied with 1 by e. So it got reduced by a factor of e. So that distance is skin depth. So skin depth is this much. Okay, fine. So I don't think there is anything. Uh, and beta approximately we know it is this much. So they're substituting it here, right? Yes, they're substituting it there. So skin depth formula. I think these things are probably necessary, but they won't ask you to write the exact value of alpha. Okay, there is some example you can go through it. There is one more. This is mu. I think this is frequency. Okay, this is for copper. Fine. They just substituted the values. Here there is this one mu is given, sigma is also given. So they just substituted this and they rewrote this formula. That's it. So this is for copper. This is for copper. You don't have to remember this. Maybe you could just remember the main thing. If they specifically say copper, then from here only you will get this one. So you don't have to separately remember this. Maybe tutorial questions will help. I think I don't know if they ask this in the tutorial. I'll have to see. But anyways, and for a good conductor, why should this be greater than one? Because good conductor means sigma should be big. So sigma is conductivity, no? So that's why there should be a large number. We saw this quantity yesterday. It was tau in the previous case when the wave was propagating in a medium. Not previous case. I think we saw it here only. Here, see, tau is there. We saw it here only. So free charge density of volume charge density of free charge is exponentially decaying. That was what we saw. Fine. So derivations are not required. So what they're telling is they want to very sensitive detector, so powerful transmitter. Low frequency because they want to reduce this frequency. They want to reduce sigma. They want to increase. If you do that, then what's going to happen? What is going to happen? If you decrease your if you decrease your frequency, then your skin depth will increase. So that means you can travel more distance before your wave gets attenuated, before the amplitude decreases. So if you increase the skin depth, it will then the wave can travel more distance. So the reduction in amplitude will be less if skin depth is more. So that is the concept. So you want to decrease your uh, frequency. Fine. Let's see if the next PPT gets over in less than 10 minutes. So that would mean 10:57. Let's see. Where was I? Is this? Okay, fine. This formula we've seen in minor 2 electrostatics. And if you're in a dielectric medium, this will change to half d bar dot e bar d tau. All of this was there in minor 2. You can see the video. The video still exists. And for magnetostatics, see what happens is wherever you see epsilon in electrostatics, in magnetostatics you will see 1 by mu naught. Even in Coulomb's law you have 1 by 4 pi epsilon naught, but in Biot-Savart's law you have mu naught by 4 pi. So it's like they're opposite to each other. So something like that. So instead of epsilon naught by 2, you have 1 by mu naught here. We will not see what will happen if this is in a dielectric. We'll just get on with this. So this is energy, work done. The energy, magnetic energy. This is electrical energy. Fine. So what is total energy? Electromagnetic wave has both electric field and magnetic field. So total energy is basically summation. But this is not total energy. They are dividing total energy per volume, right? So if you divide by volume, then this volume will get away. So you will only have what will you have? You'll have this one half epsilon naught e square. The other one is half b square by mu naught. So half is taken out common. So you can call this the energy density because energy per unit volume, energy density. Okay, now they're trying to do something. They have a charge q that is moving by some distance in some time with some velocity. This is my force, right? Electrostatic force, and this is force due to electrical field, and this is force due to magnetic field. They're doing all those things. This will become zero because v cross b is perpendicular to v. So if you do dot product, this will become zero. Fine. So finally, what did you get? You got this one and this one. Okay. So what is all this? F dot ds is work done. So work done per unit time is equal to this much. What is this? If this is volume charge density, Q is volume charge density into volume. So that will give you the charge, right? That is fine. Uh, I know J is this one. How do we get this? Mm, let me see. Mm, maybe this comes up in minor two syllabus, wherever we were discussing Ohm's law there, or maybe Hall coefficient somewhere over there. I don't remember. Maybe there we'll get to that. This was basically this is current. This is uh, what is this number of charge carriers per unit volume. All of these equations were in Hall's coefficient, Hall effect. Somewhere over there, I think this pops up. This was area of cross section. This was drift velocity. So drift velocity. I'm thinking, can how can I use this to get this? Not this, but this. We can think about it later. We were like less than 10 minutes, no? So just look into how from where did this come. I'll just consider this is true. Or okay, should I spend 1 minute here? Mm, let me see. And J is nothing but This one, so I is nothing but, mm, I'm simply writing equations at this point. How do I reach that? And I is nothing but dq by dt, which is nothing but, so no, I'm going to rediscover continuity equation. I won't reach anywhere because continuity equation was something like this. No, this is nothing but Gauss divergence. Okay, I at this point I simply rediscovered continuity equation. Continuity equation was this, no? Minus, you get a minus sign for some reason. I'll not go get into that why and something. Okay, anyways, this is taking a lot of time. So we'll just consider this is true and we'll just go ahead. So what happened? Mm, they replaced Q with rho d tau and E dot V. V is nothing but J by rho. Is that what happened? And rho gets cancelled. Fine. So after some substitutions, you get this. So work done per unit time is E dot J into, fine. From these two equations, I wonder from where did we get this. I'll have to look into it later. Maybe if someone reminds me after the class, we'll see. Okay, we have so much to cover in this. We'll see. Uh, what is E dot J? And J, I know J is omega sigma, right? Where are we going with this? So if they send the volume to the other side, it becomes E dot J, right? So work done per unit time per unit volume. So they're telling power. Work done per unit time is power. So power delivered per volume. Now from where did this come? Mm, oh, this is one big thing. This is one big equation. From where did we get this? This was this was here, no? This is a small u. Wait, here an integral is missing altogether. I mean, where is the variable of integration? So d tau. So this is small u. This is uh, energy density. They're integrating it with respect to volume, so you will get your energy now. This energy density, you will get energy, total energy in the volume. So this is energy density. You'll get energy if you integrate it with respect to volume. And then you're differentiating with respect to time. So energy per unit time will be power, energy, rate of change of energy or work done or whatever. whatever you think. They have the same units anyways. So this will give you power. What is happening here? Mm, fine. So I think it's like a theorem. I don't see how we came here. Oh, it's 10:58. So I've spent more than 10 minutes here. Let us go through it fast then. Faster. Okay, fine. This equation is called Poynting theorems. Okay, let's see what does it have to say. Probably we understand the right. This right side part is power. From where did this come? This is some. They're doing some integration on the surface of the volume. Okay, let's see. Poynting theorem. Work done for green times with power. Yeah, on the charges by electromagnetic forces equal to decrease in energy in the remaining fields, less the energy that flowed out through the circuits. Okay, maybe it's like some energy is going out of the volume, so that in order to capture that, they're doing some integration on the volume. But I wonder, what is the context altogether? Okay, the context is this one: some charge is moving through some distance in some time with some velocity. Fine. So some charge is there, it is moving some distance in some time with some velocity. That is the context. Fine. That was the context. Is it still the context? I have no idea. Hmm, maybe now they're shifting the context to some electromagnetic wave moving, propagating through some medium. Maybe that is the context now. Suddenly they shifted the context. But let's see. I don't know. Energy point. Fine, they defined something called pointing vector. What does this give me? What do you think are the units for this? Maybe then we'll get some idea. Units for this is volt per meter. Units for this is Tesla. Tesla is nothing but what is Tesla? Is it this? Let me see. It is Tesla, but what is Tesla? I think this is Tesla. I think yes. So that is Tesla. Fine. And its mu naught is So what will this give me? Volt per meter square. No, volt, there's ampere also. Volt ampere per meter square. Volt is nothing but joules per coulomb. Coulomb second is nothing but ampere, so that will go. Joule is nothing but Newton meter. Newton second per meter. Does it give us any intuition? Or we'll keep the joules? Or did we get the units wrong? I wonder. Maybe just look at the units yourself. Or I could just Google, right? What is Poynting vectors units? I think we got the units wrong. It seems the second should be in the denominator. How was that? Volt meter. Okay, fine. So you can look at it later. Apparently, the units of S is watt per meter square. So watt is power, unit of power. Meter square is just area. So power per area, I think. So Poynting vector. Okay, fine. Energy flux density. It is called energy flux density. Fine. We know what is Poynting vector, and that appears here. This is Poynting vector, right? So dw by dt is minus mm, s bar dot da bar minus dou by dou t of, we're integrating u. Fine, I rewrote this. We know what is s, we know what is u. This is t. Fine. So maybe this is Poynting's theorem. Work done on the charges by electromagnetic forces equal to the decrease in energy in the remaining fields. Okay, they wrote it. Okay, I don't have to write it. They wrote it for me. They rewrote their thing for me. Nice. And what is happening here? Gauss divergence theorem. Fine. So what is the context? It's like maybe some electromagnetic wave is moving. They're trying to calculate what is the rate of change of energy. That is what they're trying to calculate. Somehow this Poynting vector pops into the picture. This right side we understand. Right side is nothing but there is energy density. You're integrating with respect to volume, you will get energy, and then you're differentiating with respect to time. So there you're getting rate of change of energy. But the Poynting thing is an extra addition. Somehow it comes into the picture. I don't know why, but it is coming into the picture. This is fine, but Poynting vector comes into the picture. And somehow minus sign is also there for some reason. In empty space. In empty space, what do you mean in empty space? In empty space, what's going to happen in empty space? You'll have nothing. This is zero. Fine. Empty space when it is zero. What is the reason? So rate of change of energy density is minus divergence of Poynting vector. Fine, fine. So this W, it was representing the work done by electromagnetic field, right? On the charge or something. So I would like to assume that in empty space there are no electromagnetic waves, so no work will be done. So this is zero. I'll assume that. I'll just assume that. But some I don't get the context. But fine. We'll just move on. It's already 11, 8. It was like 10 minutes per slide, and this is the situation here. This is okay. Fine. There was continuity equation, which was this one, right? We had this, and now we have this. We have continuity equation for energy. This was continuity equation for charge. This is continuity equation for energy. Again, in free space, I think. This is for in free space. In the other case, a continuity equation in free space. In free space, you'll have no charge, so I think this is what we consider. I think. I think. Do not take my word. I think. Fine. It can be shown that this was a magnetic field intensity, right? B bar is magnetic flux density. We've been calling this magnetic field, but it is actually magnetic flux density. H bar is magnetic field density, and this is how they relate. And K is the wave vector, parallel to the direction of propagation and perpendicular to both B and H, B and E. I mean, this is, I can just send this here and write it like this. B bar is K bar cross E bar by omega, because H bar into mu is nothing but B bar. But they want mu to be in the denominator because epsilon is in the denominator as well. That's why they wrote it in terms of H bar. That is fine. Because if you look at the magnitudes, uh, K is nothing but 2 pi by lambda. Omega is nothing but 2 pi mu. Epsilon is there. H is nothing but B by mu. 2 pi gone. What is happening? So mu epsilon. Uh, Mu lambda is nothing but C. And I know, is this even valid at this point? C square is 1 by mu epsilon. Fine, so this is BC. Fine, yes, this is correct because I know E is BB, or in this case C. So magnitude, okay, fine. The magnitudes are correct only. So these equations are correct. You can verify. Fine. For a plane wave with E, you can check the directions also. If K is here, direction of propagation. If E is like this, K cross uh, K bar cross E bar will be, if you use right hand rule, you will get B or H, whatever it is, because B is nothing but mu H bar. And if I have E bar, no, if I have B, can be anywhere. If I have B, if I have K, if I do right hand, if I use right hand rule, I will get E. Fine. We this is nothing but we got it from there now. We know that in uh, in a medium, not conducting medium, just a normal medium, maybe free space or whatever, in a dielectric medium or whatever, in some normal medium, it was something like this, no? E power minus I omega t minus k. Yes. So if it's in a conducting medium, then you know that you will get some extra factor. Some extra factor will come and this k will become alpha. Extra factor was this one. The wave will attenuate. Fine, if E is given, I told you, no, you have to take the real part of E bar. So if you take the real part, you'll get cos. That is why cos is there. And if you're moving in z direction, then R bar is nothing but Z bar. Z bar is nothing but Z Z cap. So if you know E bar, you should be able to write H bar as well. So how do we write it? If we know E bar, H bar is nothing but this one. So you get K omega mu, that is fine, K omega mu, and you will write E again, E you will write, but direction will change. So direction will be perpendicular to K bar and E bar. So if your E is along X cap, so and K is along Z cap, K bar cross E bar will be Z cap cross X cap. What is this going to be? I J K. Uh, so Z cap cross X cap will be Y cap. So this will be Y cap. So that's why Y cap came here. So magnitude you can directly write. Magnitude is nothing but mag magnitude of H is nothing but K omega mu. Or else you can start finding your magnitude using this formula and this formula. You can get all of your magnitudes. If you have E magnitude, you can get B magnitude. If you have B magnitude, you can get E magnitude. So the same thing they wrote it like this and like this. If you want to memorize, you memorize, or else uh, this is one way of finding magnitudes. But if you find magnitude, that's not enough, right? You need direction as well. So direction means E is all three of them are mutually perpendicular. So keeping this in mind, you can find direction however you want. So if you're using this one, magnitude is nothing but k by omega mu. E is there, so you write E as it is. But direction will be given by the vector, no? So k bar cross E bar. K bar is along Z cap, and E bar is along X cap. Its cross product is Y cap. Fine. So H also we will now be able to write. And this is still in one dimension. I mean, X cap, it could be some other vector. You can have a bigger in the sense you can have some 5x cap plus 3 y cap or whatever. And if you notice, we saw pointing vector was nothing but 1 by mu naught E bar cross B bar, right? But I told you B bar is mu by H, and more specifically, you can open this. You have multiple ways of writing this. One way of writing this is H bar plus M bar. So if M bar is 0, then you can write B bar as mu naught H bar when M bar is 0, where M bar is magnetization. So they replaced B bar by mu naught with H bar. Fine. Now you know how to write E bar, you know how to write H bar. So they now substituted this in the pointing vector, you'll get S bar. Nice. What are the changes? You're just squaring the E now, because if you look at the magnitude, what will you get? You'll get E, you get E magnitude, you'll get H magnitude, and since the perpendicular sine 90, so that is fine. And H magnitude, I'll write simply now. H magnitude is basically k by omega mu. I'm writing from here, k by omega mu. Or else you can there are some multiple ways to remember things. Whichever one is better, I would start from here, but whichever one is easier for you, you can go through it. So magnitude will be something like k by omega mu e square. So that is what they got, k by omega mu e square. Direction will be along the direction of propagation, because e bar e bar was along x cap, h bar was along y cap, x cap cross y cap will give you z cap. So you got z cap, and z cap was the direction of propagation. So x cap, this is e, y cap, this is b. So oscillating, they're all nice. I was like 10:58 and now it's 11:20. Okay. Okay, what does pointing vector represent? It's the its units are watt per meter square, or else you can think of it like joules per second meter square. So it's rate of change of energy per unit area. Okay, so it's like intensity, isn't it? Intensity is work done per unit time per unit area. So pointing vector is like intensity. It represents intensity. So work done per unit time per unit area will give you intensity. So intensity will have this unit. So pointing vector is essentially intensity, I believe. So they're trying to take the average of course. Okay. Oh, okay, intensity, no? So maybe they want to find average of S. Did they do anything here? Nothing as of now, I think. Okay, fine. Average of cos square, isn't it half? I think it's half. Maybe, I don't remember. Let's see. Energy density, fine. Okay, fast. You're going fast. If you know E, you know how to write B. Okay, they're substituting these values in U. Okay, this is the magnitude. Fine, we have the magnitudes. They're replacing. Okay, fine. So. Okay, from after some calculations, what they showed is the electrical energy and the magnetic energy, both of them are the same. Since both of them are the same, I could say total energy is twice of this, so total energy is twice of this. Or initially we told total energy is electric plus magnetic energy per unit volume. So energy density. This is energy densities. If you want energy, you have to integrate it with respect to the volume. Then you'll get energy. These are energy densities. Nu is energy density. Energy density. And they're substituting the magnitudes. Fine. Okay, this is the average energy density. So, and average of cos square is half, so it just disappears. And both of them are equal, so if they are equal, I can write it as mu is equal to epsilon naught e square cos square whatever. So average of mu will be half epsilon naught e square, because average of cos square is half. If you want, you can integrate and see. In some time period, I think uh, cos square average is half. Maybe just if you want, you can look. Cos square time period is pi, so look into this. Is this half? I think maybe it should be half. And I know this is also equal to 1 by 2 mu naught b naught square. So this is the average energy density. Average. Yes, so intensity. Yes, energy per unit area per unit time. This is energy density into velocity. Okay, velocity. What will velocity give you? Uh, Energy per volume, distance into time. Energy is joules, volume is meter cube, distance is meter, time is second. What's going to happen? This will become square. So, okay, you're getting the same thing. So, energy per unit time per unit volume. So, intensity. So, if you multiply energy density with velocity of the wave, you're getting intensity. Energy density, I'll take the average energy density. Average energy density is this much. This is average energy density. So this is average energy density into velocity will give me my average intensity. Average intensity. So I think there were some questions, like maybe in the tutorial or something. I don't remember. Find the intensity. I think we did some questions in class as well, so you can remember this. You don't have to remember the derivation. This is fine, and the fact that this is average energy density, fine. Should increase the speed. Uh, what is here? Okay, the same thing. They give some example. You can look into the example. So they gave you power. They want you to find intensity. They gave you distance. So there is some bulb, and they want you to find the intensity at 10 meters. But if a bulb is turned on, light will spread in all directions. So you'll get a sphere of some sorts. Intensity is nothing but power per uh, area, right? Because power is nothing but work done per unit time. So intensity is work done per unit time per unit area. Work done per unit time is power. So power per unit area. So power per area will give me intensity. So what does it mean? Because if you're closer to the bulb, intensity is more. If you're going away and away, the intensity is decreasing. Why is intensity increasing? Because light is spreading. Light is this area is there, no? It's spreading. So initially, all of that was concentrated here, so intensity is high. But as if you go farther and farther away, the area, the spread, like the light is spreading, right? That area is increasing, so intensity is decreasing. That's why as area increases, intensity decreases. So the area of this sphere is 4 pi r square. So power by area is this much. So this will give you the intensity. And if you know the intensity, we know how to find the electric field. So intensity we have, epsilon naught we know, C we know, so we can find the amplitude approximately. Because this intensity is actually average intensity, but we'll just call it intensity. Because this is the average uh, energy density. Fine. Okay, they gave another example. Power per, they themselves gave the area. Fine. Very high intensity. use the same formula above. Where is this? Use the same formula, you can get your electric field. You can get even H naught now because we know what is the connection, or B naught as well. We know what is the connection between E naught and V naught because E is nothing but VB, or CB in this case because velocity is C. We can find the magnitudes easily. So why are lasers dangerous? Because the electric field is comparable to the interatomic forces. So they will interact with the atoms. And what happens when you interact with atoms? The properties will change then because now the atoms can be split apart. Not atoms splitting apart. Molecules can be split apart, and all those things will happen. So that is dangerous. That's why it's dangerous. Okay, boundary conditions. Okay, where are we again? So this is the right one. So previously they were not writing this free one. Now they're writing free. Nice. This is Ohm's law. Because previously I think they considered p to be zero. If p is zero, then rho is nothing but if p is zero, p bar is zero, rho bound will be zero. So rho is nothing but rho free. This is an accurate description. This one appears in minor two portion. So if you remember, you can see the video is there on that. So you can see still there electrostatics. Anyways, electric field, magnetic flux density, electric displacement, magnetic field intensity are discontinuous. Okay, fine. We looked at the discontinuities of E and D in minor 2. Minor 2 may we saw all of that. Uh, Current density. Like we have J, we have K, we have lambda. This is the volume current density. This is the uh, surface current density. Yes, and this is line current density. Yes, yes. All of this was in minor 2. This was not in my videos, but I think this was in minor 2. Maxwell's equations. Fine. All of this is fine. This is Maxwell's correction. Okay, what is happening here? Is there anything new that I have to see? Integral form. Okay, fine. We know that. Q free enclosed. Integral form. Is there anything new? No. Integral form. Everything is integral form. Fine. Okay, they want to use the integral form in the boundary conditions. Maybe it's easier that way. Fine. Uh, what are they trying to do? I don't think we have to go through the derivations. We'll look at the result. What is the result? We know this. We've seen this. Perpendicular components of the electric displacement, they're discontinuous by this much. Okay. Now we have discontinuities for the magnetic field, or more specifically magnetic flux density. Perpendicular components are not discontinuous. Okay. Okay. Fine. Strange math happens, and then finally what happens? Okay, we need to know the context. So what is the context? Over a closed surface S. So if there is any surface charge, or let's say this is some surface, if there is any surface charge density, then the perpendicular components of D will be discontinuous by this much sigma F. Will not derive. You can we've seen it in the video previously, and I know D bar is nothing but epsilon E bar. So d bar dot da bar, that is nothing but the flux, no? That is the magnetic flux. So magnetic flux is zero. Fine. We did something like this for the boundary conditions for E bar and D bar. We did something like this. And for tangential component, E is also continuous. Perpendicular components, I think it was differing by sigma by epsilon, right? E E perpendicular minus, it was differing by sigma by epsilon naught. And we saw D is okay, D perpendicular is differing by sigma f. E parallel is same. Is there D parallel anywhere? Oh, okay, fine. They wrote it for us in one place. Okay. What was D parallel again? Were they the same? Did they mention anywhere? Okay, fine. Just look into this. You'll find it in minor two syllabus. Somewhere it's lying. Here, what did they write here? So T, where is T? So T is some random direction. Fine. Mm, is it tangential? Is T tangential? So are they trying to tell me H1T or tangential in the sense perpendicular? Is this what they're trying to tell? No idea, but I highly wonder if they'll ask us this, but who knows? Boundary conditions. Mm, if current is not there, that is fine. You'll get zero only. That is absolutely fine. Let's look at the summary. This is okay, fine. This is maybe fine. Tangential components are equal. Perpendicular components differ by sigma by epsilon. Check what happens to the parallel components. This is interesting because they're not telling me what is T bar. What is T bar? They're telling for parallel or tangential components, this is happening. No, likewise. Fine, let us. Where is my equation? This is my equation, no? This is nothing but Q free, or not Q free, but Q free enclosed. wondered. Just look into this. What does this mean? I have to see later. I'm looking at this equation for the first time. But one thing that you can see, if I is zero, then it's just simple. It's discontinuous. Like how if sigma free is zero, it is continuous. That part is fine. Fine. We'll just get on with this. We'll look into this later. Okay, 11:39. Let's see if we can finish this in. No, there's nothing here. Fine, 11:39. What is here? Okay, there is some surface. Some wave is approaching with EI electric field intense whatever. This is the amplitude of electric field. This is the amplitude of magnetic intensity field. It's going. Finally, what happens when it interacts with the surface? Some part gets reflected, some part gets transmitted. So you have new amplitudes. Why does this happen? Because now imagine instead of a surface, there is a new medium altogether. So there is a new medium here. That is what is happening. You have a new medium here. How is it a new medium? Because your epsilon and mu are changing. Why do you think H went that side? Because if you notice this property, there's what is this? The directions, how are they? If you take the cross product of E and H, if you take cross product of E cross, if you take this product, you have to get back your direction of propagation. That's why H went that side because this is your direction of propagation. H will not remain here. So if your incident wave is looking like this, if it looks like this, if it goes and bounces back, if it gets reflected, then H will go to the other side. H will go to the other side. Other side in the sense now this will start oscillating from here now, but it won't be H won't be H will be pointing that way because E bar cross H bar should give you the direction of propagation. This is nothing but this one. No? Yes, this is nothing but this one. S bar, the pointing vector will give you the direction of propagation, and its magnitude is some form of intensity. Fine. So let's look at how if this is your incident wave. What is here? Here minus or plus shouldn't matter, but I will put a minus sign. Not because I want to put it, because we've been using minus sign, but it is fine. I told you why minus or plus wouldn't matter because the only change that will come is in fine. The only change that's going to come is over here, but we are only taking the real part, so this part doesn't matter. So minus or plus doesn't matter here. Okay, what is changing? When the wave is getting reflected, this is my initial k bar, right? Now my k bar it goes back 180 degrees, so it's like in the opposite direction. So you get a minus sign. So minus of minus will make it a plus. So you have plus there. And if you notice, the amplitudes are also getting changed. So we are representing them in uh, we are representing them using different variables e10, e20, and so on. This looks very similar to this because they're traveling in the same direction. So the k won't get a minus sign, but its value changes. Why does it change? Because we know k is this one, right? We know k is 2 pi by lambda, but we also know this is the case. How do we know that? Because lambda is nothing but c mu, and this is nothing but omega. C is nothing but see wherever you go, you just keep going in circles. Everything is connected at this point. Fine. So, but here h will change, right? So if hi is there, if there is an equation for hi, how do you write hi? Maybe it's there in the other slide. We'll just go there. Hopefully. Let's see if there is hi in the other slide. Back. No, 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 no. Is there h? Okay, yes, they wrote h. Fine, nice. I didn't have to go through the trouble. This was third Maxwell's equation, right? Like third or whatever be the number. So they're doing some derivation. After doing some derivation, what happened? They got your equations for h. I mean, uh, I mean, you don't have to do all of that as well because I know E is CB, B is nothing but H mu, right? B is nothing but H mu, and C is nothing but 1 by under root mu epsilon mu H. So what do you get? Mu by is this what you get? So H is nothing but epsilon by mu E. Well, see, that's the same thing that they got. You don't have to break your head or something. This seems to be very helpful in some cases. Most of the cases, probably. Fine. You get the same thing. Fine. So I don't have to go through. Okay, and this one also, we know this is true, right? Fine. Whichever, whatever you do, finally you'll get something. What is it? You have this is your magnitude. You have your magnitude of h. Direction is also given here because y cap, no? This is y. It's given. Okay, this is y. This is x. This is z. Fine. Now, if you have hi, how do I write the reflected one? If you notice, the reflected h changes its direction. The reflected h changes its direction. So here you will get a minus of minus means plus. You'll get a plus sign. The k value didn't change because in reflection you're traveling in the same medium, right? So incident and reflected wave are in the same medium, so k won't change. So k is also same. K will change in the other medium because k is dependent on the medium. K is dependent on the medium. Are there any other changes? Okay, so minus sign. So here you get a minus sign, reflected one. It changes the direction. Previously, okay, see, E and all don't explicitly change directions, right? They're still in the same direction. Here, the only thing that's changing direction completely, one is K, the reflected part of the K is changing directions, and the other is the H, the reflected H is also changing direction. So that is why you get a minus sign. That's why we got extra minus sign, minus minus plus. Here also minus minus plus, and here you get a minus sign because it flipped. It flipped. These are E values. These are H values. B is nothing but mu H, so that B is also easy to find. Mm, This is the curl formula. For some reason they kept. Maybe they used it here. So they used the curl formula to directly find it out. I think. I mean, this is just one dimension, so it is maybe simple, but when you have multiple dimensions, maybe you have to be careful. Like instead of kz, you will have minus k bar dot r bar, so you can have anything there. Uh, Okay, they're saying the sum of amplitude should be equal. This was incident, this was reflected, this is transmitted. Maybe all of this is for conservation of energy because energy is proportional to amplitude square. Okay, not E. We'll use uh, not even E. Fine energy, I'll write energy is proportional to amplitude square. In order to conserve energy, maybe they're trying to say incident amplitude plus reflected amplitude is equal to transmitted amplitude for some reason. Now don't get me on the non-linear relationship. I'll not get into the details. So if you do what do you do? Derivation. This is the refractive index formula, right? Because refractive index is C by V. C is nothing but mu naught by epsilon naught under root. V is nothing but 1 by under root mu by E. Mu and mu naught are almost equal, so you get epsilon by epsilon naught. Yes, so that is what they were trying to do. So what you're supposed to remember in this is this one and this one. So this is the intensity of the reflected wave. This is intensity of the not intensity. Electric field of the reflected wave, electric field of the incident wave, electric field of transmitted, electric field of intensity. So you have the ratio of amplitudes of electric fields reflected to incident and transmitted to incident. So this is like uh, you have to remember this. So if n1 is smaller than n2, then you'll get a negative number. But don't worry, that if you get a negative number, it means the amplitude flipped. So that is the meaning. If you get negative numbers, don't get confused. But don't write n2 minus n1, then that will change the entire story. Here, will you get a negative number? No, you'll never get a negative number. What does it mean? It means that in whichever direction E incident is there, in the same direction E transmitted will also be there. So there will be no flipping in that case. Okay. Incident, this is pointing, no? They're taking average of pointing. Pointing units were watt per meter square. Power per area will give you intensity. So incident wave intensity is proportional to the time average of pointing vector, which is understood because units are watt per meter square. So it is very much understood. Okay, so incident wave intensity, reflected wave intensity, transmitted wave intensity. Fine. Okay, two new terms, reflectance and transmittance. So reflectance is the ratio of reflected wave intensity and incident wave intensity. Then transmittance is transmitted wave intensity by. Okay, nice. So basically, you're squaring the ratio of amplitudes, aren't we? And here we are squaring and then multiplying with n to by n1. Fine, not too difficult to remember, I suppose. You might wonder from where we're not bothered about derivations at this point. So and okay, nice. I'm saying we're not bothered about derivations, and all of this is on YouTube live stream. Interesting. So you can solve problems with this now. You have the refractive index of the first medium, refracting index of the second medium. They're asking you to find reflectance and transmittance. Apply formula, get answer. Beautiful. Is this a property? Reflectance plus transmittance is 1. It means total intensity is 1. You're just splitting it, right? Because they're ratios. Okay, interesting. So it means if I add transmittance and reflectance, what will I get? In the denominator, I will have incident wave intensity. On the numerator, I will have the sum of reflected wave intensity and the transmitted wave intensity. By law of conservation of energy, this sum should be equal to incident wave intensity. So numerator and denominator will get cancelled and you will get 1. So I think that is the explanation. By law of conservation of energy, this has to be 1. Okay, now interesting things. Previously it was incident normally in the sense at 90 degrees. Now oblique incident, so not 90 degrees, some angle. The first time I looked at this, I thought just break it into components, then you'll get normal incidents, and the other part you can just ignore. I was thinking about this in that way, so let's see if that is exactly the case or not. What is happening? Is there anything? Okay, they're using so many things. Oh my goodness. Reflection and transmission and boundary between two dielectrics for oblique incidents. Assume propagation vectors are co-clear. Okay, fine. All of them are on the same plane. Okay, we have ET. Okay, see, they have K bar dot R bar. I would put a minus, but fine, they're not using it, so I will also not use it for now. Mm, Now, what are these terms? X sine theta 1. So that is this direction. X cap is this direction. Sine theta 1 will give me this. Z cap cos theta 1. Okay, fine. This is the magnitude and this is the direction. That's it. Nothing much is there. So this is a vector quantity. The k vector, the wave vector. I know the magnitude of this, which is this, and now they're writing the direction as well. The direction is basically this direction and this direction. This direction is what is this direction? Cos theta. This is cos theta 1 z cap, and this is sine theta 1 x cap. So that is why. Okay, yes. So fine. Yes. So these are the directions. You apply vectors, vector knowledge, you will get these directions as well. Fine. Direction, see, if you've already written the magnitude, then your direction should be a unit vector. Is this a unit vector? Sine square theta 1 plus cos square theta 1 is 1. So, okay, fine. That is a unit vector. So, there's no problem. Absolutely no problem. Because if you're writing the vector, you write its magnitude and then you have to write a unit vector. That is a unit vector. Fine. Beautiful. Uh, so, okay, what are they doing? Here also, you have the magnitude and they're writing the direction. I is in E10 is basically this one, no? So what is the direction? And this is the vector representing the direction of incident wave. What is the direction? This is the direction. If that is the direction, then how do I break it into components? I will get this one and this one. What do you mean by this one and this one? So this is theta 1. This is theta 1. So what is this direction? This is cos theta 1 x cap. This is sine theta 1 minus z cap. So you have minus z cap sine theta 1 x cos theta. Yes, fine. So we're just breaking it into components. That is also fine. Now what is happening? Are they doing anything? Why did they write this separately? Any reason? Any reason? If you notice, they have changed this, right? They multiplied it with a minus sign for some reason. And that shouldn't be a problem, should it? It shouldn't be a problem, but you should be consistent. You can't simply multiply whenever you want to. Okay, these are in the same direction, but then E reflected is slightly different. Okay, how do you solve these problems? It's like this is the direction of propagation of incident ray, this is the direction of propagation of reflected ray, this is the direction of propagation of transmitted ray. So if you break it into components, you can think of it like this one. E is some part is normally incident, some part is simply going to the top. And even here, E can be broken. How is E? E is like this. Interesting. If E is like that, and here E is like this, this part is fine. It's going to the top, but it looks like this E got flipped into this direction. There is a flipping. Fine. We'll just see what is happening. Is there anything that you can? There is a flipping. Is that the reason why this is k bar dot r bar minus omega t and this is omega t minus? Is that how you flip? You will flip it here, no? Why would you flip it here? Mm, and where is h? What is the direction of h? They wrote h here, so is h coming out of the plane? What is the direction? Uh, if I do e bar cross h bar, I should get the direction of wave propagation. No, h is into the plane. Uh, if h is out of the plane. Here h is out of the plane, and here h is into the plane. So h flipped. Okay, fine. It's like if you hit something, then h flips. The reflected h always flips, I think. And then what about this case? This is still into the plane. Into the plane? No, out of the plane. I'm just using this to check if I'm getting back my wave propagation direction or not. I think we're spending so much time here. Is there anything that this wants to tell? Are they using boundary conditions? Fine. Tangential component. Tangential component of E was continuous. Okay, I know law of reflection. This is Snell's law. That is also nice. So, what do they want to tell? Are they even solving it at this point? No, they're not solving. So, okay, we don't have to break our heads then. But it looks like a good question. If they ask it, it will be a super hit. But I don't know because they did not proceed solving it or something. Fine, I'll just proceed with this. You can sit and think about this. If it's in the tutorial, I don't know. The best thing you could do is go through the tutorial for questions and see if you're able to solve it on your own without any help. I mean, you can take help, but if you understand what is in that, that is fine. If you don't understand, then that's a problem. Okay, law of reflection is fine. Snell's law is fine. Where is Snell's law used? It's used in cases when refraction happens. So you will get to know the angle of refraction. So let's say this is some medium 1, this is some medium 2, some light is incident, and some light gets transmitted. So incident, angle of incidence, angle of refraction, nice. So Snell's law dictates this. Now, what is Brewster's angle? We saw there is something called critical angle. Critical angle, did it come critical angle? I think it will come after this. Maybe, I don't know. Did we cross critical angle? I don't remember. I remember taking a class, no? That their critical angle was a total internal reflection. It's like you're in some medium. What kind of a medium? If you're in some denser medium, and if this is some rarer medium, then this will happen. This is some theta incident. This is some theta. So if you keep increasing this, at one point your light will go like this. So this is your theta critical. That is critical angle. If if you go above your critical angle, then you will get reflection. This is total internal reflection. There was some slide about this. But anyways, now there's something called Brewster's angle. What is Brewster's angle? They will okay. What is theta three? This is theta three. Fine. Theta three is pi by two minus theta one. This is pi by two minus theta one. Why should theta 3 be equal to pi by 2 minus theta 1? What does it mean? It doesn't mean anything, I think, right? We'll see. We'll see. Let's say incident ray is theta 1, refracted ray is theta 3, and they're saying if this is equal to pi by 2 minus theta 1. Is there a better picture? What does it even talk about? What is the okay? I think maybe there is some property. If theta 3 is equal to pi by 2 minus theta 1, something special happens. What is it? So sine of pi by 2 minus theta 1 is cos of theta 1. Fine. So theta is nothing but tan inverse n2 by n1. But what is happening? Okay, so Brewster's angle is the angle at which when an unpolarized ray of light is incident on a surface, the reflected ray will be linearly polarized and the transmitted ray is partially polarized. Maybe some special thing happens here. This is a special thing. So Brewster angle is the angle at which the incident at which an unpolarized incident ray of light gets reflected as a linearly polarized ray of light, while the transmitted ray of light gets partially polarized. Interesting. And okay, they have notation perpendicular component. So all the parallel components are gone, got blocked. Fine. Okay, picture is there. All these parallel components got blocked. Only perpendicular components remain. Brewster's angle. All of that magic came from here. So theta 3 has to be theta 2 minus the pi by 2 minus theta 1 for some reason. I was like 10 minutes per slide, and what is this? Okay, critical angle got its mention over here. The last slide. So critical angle is sine inverse this one. Brewster's angle is tan inverse this one. Is that how it goes? Yes. Critical angle, I told you. This is the story here. It is understandable. At some point, your ray will come here. So if you cross your critical angle, the ray will not be get transmitted. You will get reflection. So that is total internal reflection. For that, I think you have to be in a denser medium, and outside should be a rarer medium. But this is a critical angle part. Brewster's angle is a different thing. Maybe because of this relation, this property is coming into existence, or it's it's showing itself. Theta 3 is equal to pi by 2 minus theta 1. So this is no, not this. This is equal to pi by 2 minus theta 1 if this is theta 1. Is that how it is? No, 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 no. That is tan inverse 1. Yeah, that is not how it is. Oh no, it is. It is how it is. It is how it is. Yes. So if my incident ray of light is theta p, and if this is pi by 2 minus theta p, that would mean this is theta p, this is theta p, this is pi, this is pi by 2 minus theta p. Is this is this leading us somewhere? No, it's not leading us anywhere, is it? It isn't. So some magic is happening here. So at Brewster's angle, the reflected ray is linearly polarized. That's it. I don't see any other reason. Again, formula for the refractive index. Fine. So I think all of this was basically because they want to talk about what is Brewster's angle. I think all of this. Fine. But if they give that as a question, that would be super. But I don't think they will give it as a question. But do not take my word. Some math you're doing, fine. It is simple math. This is also fine. I told 10 minutes per slide and take okay 12 12. Will the next slide will the next PPT get over by 12:22? Let us try 12:22. Let us try. We've seen this, and all of this is fine. Total internal reflection, there's nothing. It's all about critical angle. Brewster's angle, maybe we'll have to just see mm, some phenomenon that is where the reflected ray gets linearly polarized just because the incident angle is equal to Brewster's angle. Interference. Consider superposition. Okay. Considered superposition has been considered. Okay, fine. Non-identical. So amplitude is different, phase is different. This is a phase, no? This is phase. How is phase different? I mean, phase angle. These are phase angles. So your phase angles are different, but they have the same frequency. Fine. Here, phase is different because the phase angles are different. Okay, they did something. Resulting displacement. You just sum them up because superposition, right? What do you get? Okay, they're considering this to be semi-cosine. Okay, okay, nice, beautiful. What do you get at the end? Okay, they get if you have x1 and x2, they're adding them. You're getting a final resultant wave. You got a resultant wave, but this theta is magical. What kind of a theta is this? It is given by this equation. Tan theta is equal to so and so. And is there any other new term? Okay, A. A is also there, no? A is new because we have A1, A2, theta 1, theta 2. Tan theta is given by this relation. A is given by this relation. Interesting. So what is this? Is nothing but this is phase difference because if I take the phase difference, I will get theta 1 minus theta 2. So this is phase difference. So they're checking if phase difference is 0, 2 pi, and so on. Okay, so if phase difference is a multiple of 2 pi, the amplitude is basically the sum of the two original amplitudes. And this is constructive interference. And if the phase difference is an odd multiple of pi, then the resulting amplitude is the difference, assuming A1 is greater than A2. Or else you have to take the mod. That is not a problem. Because when this is the case, you will get A1 minus A2 square under root, right? So this is nothing but mod A1 minus A2. So that will take care, but here they did not put mod, so that is assuming A1. They assume A to be always positive. I mean, it is always positive. Amplitude is positive. It can't be negative unless you're flipping it, right? Fine. Constructive interference, destructive interference. What did we learn? Here, phase difference. This is my notation. How I write phase difference. Phase difference is a multiple. So how do you write multiple of 2 pi? So it's a multiple of 2 pi. In this case, phase difference is a it's an it's it's not any multiple. So it's an even multiple of pi. That is one way. Here it's an odd multiple of pi. I can write it this way. Fine. So this is for constructive interference and this is for destructive interference. So I told you right previously path difference is phase difference is nothing but 2 pi by lambda path difference. So in this case, what will be the path difference? So it will be lambda by 2 pi into 2 and pi, 2 pi, 2 pi. So path difference must be n lambda in this case, and phase difference must be lambda by 2 pi, 2 plus 1 pi, pi, pi. Or what is this? N plus 1 by 2 lambda. So what is this? So it's like odd, okay, yeah, or else you can just leave it. So this is like odd multiples of lambda by 2 to get destructive interference. I think write it somewhere. Okay, they'll write it later probably. This will appear somewhere. So later, I mean, they didn't show it probably. So at constructive interference, intensity is maximum because amplitude is maximum. If amplitude is maximum, energy is maximum. That's why intensity is maximum. Okay, you get something called interference pattern. Fine. If you're using two independent waves, then it's very difficult to ensure that they have the same frequency and all those things. That's why if you use the same source, it means uh, they'll have the same frequency, they'll have the same uh, phase as well. I think that is probably what they're looking for. Let's see. Mm. Yes, so constant phase relationship. Constant phase relationship. What is phase? It's uh, this is phase, right? That is phase. So if the phase between these two sources, not sources, between these two waves are same, phase difference will be phase difference will be what? Zero in that sense. If phase difference is zero, then amplitude will always. We'll see. We will see. Division of wavefront. Wavefronts are basically it's like if you have a source, uh, it is considered it moves in the form of wavefront. So this is called a wavefront. I think Huygens gave this principle probably. Division of amplitude, multiple beam. Okay, so there is one. Okay, not one. There are two sodium lamps. So you won't probably be able to look at an interference pattern because you're using two sources. We want to use one source because if you have constant phase, it is easier to notice. I think the explanation to this will be given later. I think, or it will never be given. But if you use different sources, then you can't guarantee. See, if you're using two different sources, we know amplitude may change. So many other things will change. Omega might change, theta might change. But if you're using the same source, then all of this will be constant. So we can focus on the interference pattern in that case, or else maybe we won't be able to notice the interference pattern for some reason. So we'll not get into the reasons. Hmm. So the takeaway from here is if you're using multiple sources, then you won't be able to notice the interference pattern. We're not talking about whether it will happen or not, but you won't be able to notice. Human beings won't be able to notice. Okay, single source is there. They're just using holes to to uh, to mimic two sources, but it's actually one source. But they're mimicking now. This will act as one source. This will act as one source. But the benefit here is they have a constant phase because they came from the same source, so they will have the same properties. These are the wave fronts that I was talking about. These are called wave fronts. This is one wave front. This is one wave front. Okay, nice. Nothing else. So, and okay, uh, capital D is the distance between the barrier and the screen. Okay, there is notation barrier and the screen. Small d is the distance between the pinholes. This pattern is called fringe pattern. I think we will come to that. There's something called fringe width. All of those will come. Okay, this is the simplified form of whatever is above us. Nice. Okay, now it's coming into picture. Path difference. So maximum means if you want maximum intensity, then you need maximum amplitude. Maximum amplitude means you need constructive interference. I just showed you the previous slide. If you want Ma- if you want constructive interference, then the path difference must be a multiple of lambda. I showed this. How did you get this uh, from this one? I mean, you won't find this in the slide. This was in plus one plus two somewhere over there. So we saw what should be the phase difference for constructive interference and destructive interference. From there, we just wrote down what should be the path difference. Okay, fine. So they're substituting. What is S2P? S2P is what is S2P? Oh, did they take anything? D plus this is D. This is D by 2. This is Xn. Okay. Are they using Pythagoras theorem? Yes, so S2P square is nothing but D square plus Xn plus D by 2 whole square minus D square. Okay, fine. They're using Pythagoras theorem. And then after doing some S2P plus S1P, S2P plus S1P is approximately to do. Fine. We are not considering the angle or anything. Fine, up to them. After some derivation at the end, what will you get? We got something. So what is xn? Xn is uh, the distance from O to P. So it's like you get my point. Where is the maxima? So nth maxima, I think, something like that. So x0 would be what? N0. So x0 is 0. So the first maxima, the central maxima is here. If you put x1, you will get the first maxima. Would you get my point, right? So first, do I call it the first? Okay, if this is called the zero, then first, second, third, and so on. Minus one, minus two, and so on. Get different locations where maxima is observed. D is the distance between the barrier and the screen. Lambda is the wavelength of light. N is at which position. D is the distance between the two pinholes. Fringe width, yes. So fringe width is basically the distance between two consecutive maxima or consecutive minima. So if you have a 0 or let's say x0, x1, so this is fringe width. So all they're doing is they're taking the difference. That's it. So n plus 1 is there, n is there, fine. So this is fringe width. So consecutive maxima and consecutive minima are separated by this distance. So I think minima will be here. What do I call it? Maybe y1, y2. Let's say y1, y2, whatever. When this distance will be this much, we can show that. So bright and dark fringes will be equally spaced. So if minima is here, they will also have the same fringe width. Because what are we talking about? Young's double hole experiment. Okay, fine. Double slit, double hole, whatever. Fringe visibility. This reminds me of uh, the ratio of electric field amplitudes. It was something like n1 minus n2. But I don't think there is any relation. It's just there. Fine. Fringe visibility. So if mm, what does it mean? If my if my intensity at maxima is bigger, so maxima, my bright fringes will be more bright, right? So what would that mean? Numerator will increase, so this entire quantity, or even denominator will increase, won't it? If this increases, this will also increase. So what will be the effect? I have no idea. What if these two intensities are same? Then fringe visibility is zero. Okay. So if maxima intensity and minima intensity are same, visibility will become zero. Why is that the case? So if fringe visibility should be non-zero, then both of them should have different intensities. Interesting. Both of them should be non-zero. Fine. Non-zero in the sense the difference should be non-zero. So in someone's intensity is bigger than the other person's intensity. Interesting. This is just maybe just remember this. How do what is the fringe visibility? This much. Easier to remember. No, it's fine. Because at minima, okay, intensity at minima will be very less, right? That's why it's a minima. Intensity at a minima will be less. So fine. Intensity will be less. So this is fine. This will not never become zero, right? If it's becoming zero, it means uh, there's nothing to look at if it is equal. There's nothing to look at. You'll have a uniform intensity. That is the meaning. So if this is if intensity at maxima and intensity is at minima is zero, why is it even maxima and minima? So this will not be zero. So fringe will be visible if the intensity at maxima is higher and higher. So I think that is the meaning here. So it should be like maybe this should be low. It might not be zero, but it should be low. If the intensity is something like if the maximum intensity and minimum intensity are close, then this fringe visibility will be closer to zero, and it makes sense because you won't be able to look at fringes then. The difference should be higher. Then fringe visibility is higher, I think. Maybe that is the intuitive explanation. Fine. Why is this hyperbolic? Interesting. Sir asked this question in class. So interesting because in minor, what happened? We were discussing about the magnet problem, right? If you have a loop and both of them are like they have current or charge moving in some direction, will they repel or will they attract? That was the last question in the minor. This question we discussed in class, and he kept it in the paper. So I don't know. I'm just speculating. Will he ask why will this be in hyperbolic shape? But that's too much, no? Why is this in hyperbolic shape? Even he didn't answer. Sir did not answer. My goodness, this is going on YouTube. My goodness, my bad. Sir did answer. Uh, okay. So what is happening? So lambda. Okay, what is happening here? Let us notice what is changing. D is increased. Beta is beta is fringe width. Beta is what was the formula again? Uh, lam, what was the formula again? Yeah, lambda. Yes, right. Beta is fringe width. So if fringe width is decreased, D is increased. Okay, fine. If D is increased, beta will get decreased. That is fine. If you zoom in, fine, you'll get straight lines. I wonder why are there hyperbolic lines? Okay, we were approximating some things in our calculation, right? So only for the middle portion, you will probably get straight lines. Later, if we go farther and farther away, the approximation won't work well. So we won't get straight lines like this. Maybe if you do the exact calculations, then maybe even mathematically we'll be able to show that we will get a hyperbolic pattern. But since we use approximations, that is only true for small distances. So we will stick to the region that is closer to the central strip where you will find straight lines. We will not think about what will happen away, farther away from the central strip. Because we did use approximation. See, we used some approximation. Because of which this looks like this, or else it wouldn't look like this. It will look much more complicated. I'm assuming that complicated. equation will show us why it is hyperbolic or something. Okay, intensity distribution. What is happening? This is K. Uh, okay, and what is S1P? S1P is the distance, right? It's like when electric field came here, when the this is E1, right? When it came here, it traveled S1P distance. When this came here, it has traveled this distance in the same amount of time. So that is the meaning. So when interference is happening, E1 has this one. It looks like this. E2 currently looks like this. This is like the distance or whatever R. At point P, this is how both of them look like. So at P, it travels some distance, right? So we'll do superposition. You get something. Intensity is proportional to amplitude square. This is amplitude, right? Some constant, proportionality constant. After doing some simplification, what do we get? Uh, we This K is a constant. We did Are we given any information about what K is? No. So we'll keep K as it is. Because previously we know this one. No? I is uh, we've seen this before. So some constant. I think that is the constant, but we don't have to bother. So this is just some proportionality constant. So after doing some derivation, we got something very similar. Intensity is proportional to amplitude square. We're taking average from then what do we get? Okay, so this is the intensity formula, right? We got ourselves intensity formula. So at the point P, I1 is coming, I2 is coming, and this is also coming. And what is uh, dou? Dou here represents phase difference. Fine. So phase difference, I told you, phase difference is 2 pi by lambda into path difference. This is path difference. The difference between the paths traveled by the light rays. Nice. So cause phase difference. If you do some derivation, you will get this. K is out of the equation now. They got cancelled somehow. So it is fine. So this is the intensity. So maximum intensity, how do you find? If phase difference is uh, an even multiple of pi, then you get maximum intensity. That would mean cos dou is um, how much? 1. So that would mean intensity at maximas will be this much. If you're using destructive interference, then we know phase difference is an odd multiple of pi, and at odd multiples of pi, cos of that will be how much? Odd multiples of pi minus 1. Cos cos pi is minus 1. Cos 3 pi is minus 1. So this is your intensity at minimas. This is your main intensity formula. Mm, okay, see, we came back to the same thing. I showed you how we got this. Even there, showing you how we got this. Fine. So maxima, minima. This is the path difference. Intensity is there. Nice. So you have this. So this is a part of the syllabus. So it's no longer plus one plus two. It's here. It's in the slides. But it's not like they will give you path difference and they'll ask you what is phase difference. That will be a simple question, won't it? Anyways, mm, So this is some approximation. Is this some approximation? What are we doing? We know I is this much. If S1P and S2P are large relative to the separation distance D, then intensities are almost equal is what they're telling. Okay, if intensities are almost equal, then what should I do? If intensities are almost equal, then I1 equal to I2, then you'll get 2 I naught, 2 I naught, fine. So that's what they wrote, 2 I naught, 2 I naught. And they're using the cos 2 theta formula, no? Cos 2 theta is how much? 2 cos square theta minus 1. Yes, so that is what they're using, fine. So cos theta will be fine. So that is what they did, fine. Trigonometry, enough trigonometry. Okay, now when this is the case, when d is greater than small d, then what will happen? I can write my intensity as I naught into 4 cos square theta. Nice, so this is nice. Here, dou is phase difference, and I naught is the intensity of the light of the source. So fringe pattern looks like this. Fine. This is when d is greater than small d. Okay, they're plotting the ratio of intensity. So this is not exactly the fringe pattern, but it will look like this. It's just a ratio. If you want the original pattern, then I think you'll have to multiply everything with I naught. So it will look something like whatever is I naught value. It will go up a bit because it's just a ratio, right? Fine. Okay, okay. They give similar thought. They gave you a path difference of something. They're asking you to find I by I max. Okay, so they're making you use the formula. Phase difference is 2 pi by lambda, which is nothing but k. So phase difference is 2 pi by lambda into path difference. From here, you can substitute it in the ratio formula. You will get the answer that you require. Hmm. They're asking you I by I max. I max is, see, I max is here, no? And this is I max. When D is greater than D, I1 is equal to I2 equal to I naught, right? So I max will be this substitute 2 under root I naught whole square. So you'll get 4 I naught. So that is how you got I max as 4 I naught. Take the ratio, you'll get whatever answer that you require. Superposition of plane wave and spherical wave. Oh, this is similar to Newton's ring, isn't it? So previously in Young's double hole, we saw mm, what kind of waves they were? Plane waves? Just waves. Let's just assume they were waves. Some waves, maybe two plane waves. Here there is one plane wave and a spherical wave. But they're not, aren't they plane waves? Did they mention? Okay, whatever they were some waves. Here, plane wave, spherical wave, you get spherical patterns. Okay, fine. They gave me some equation that looks okay. So they're trying to represent this mathematically. As R increases, amplitude decreases. Is that how it is? Maybe, yes. Because most of the intensity is concentrated here, and if you go farther away, the intensity is decreasing. Nice. This is from Newton's ring. Newton's rings. Like in minor two, he simply asked, "What is the utility of Hall effect?" It came out of the blue. So maybe some some knowledge wherever in the slides it appears. Maybe just go through them because we had some slides about Hall effect within the PPT. So maybe you could just go through them there. Okay. Perfect. Hmm. Radius of M plus pth bright ring. M and P. What are M and P? Okay, they're just numbers. I think that's fine. D is this is D. Okay, fine. That is D. Whatever you say, that is D. Let's see if there's more on this. The next. Okay, there is Newton's ring. So okay, fine. Interference by division of amplitude. Wave. Okay, yes. So division of amplitude is basically when you do this, some part gets reflected, and this what will happen? So will this happen? Let's see. Okay, so here some reflection will happen. After getting inside, one more time reflection will happen. So these two rays will interfere with one another. It's called division of amplitude because when at the top surface some reflection happens, the amplitude changes, right? So some amplitude is reflected back, some amplitude is allowed to uh, get transmitted. Same story here also something happens. So finally these two will interfere, and then we'll be able to see. We'll be seeing from here. Fine, that is division interference by division of amplitude. Mm, okay, so when okay, thickness of this thin film is D, right? Okay, so when something there was a nice picture for this. Is there no nice picture? Let, okay, fine. Let me make my own thing. So we saw this previously. Uh, if it's almost normal, fine. Fine. So let's say some incident ray is there, it gets reflected, and some of it gets transmitted, right? And then it gets. Let's say this is a story. Now, what is the path difference? It's traveling a distance of 2D two times. The second ray is traveling a distance of 2D, but it is traveling the distance in an optical medium. So uh, there is something called optical distance. So you have to multiply the distance with the refractive index of the medium. So this will be the optical distance traveled by light. That is fine. So path difference is this much. Phase difference will be this one into 2 pi by lambda. That is fine. We got the phase difference. But there is an extra minus pi term. This is because when light is reflected from a surface, in a case where it is trying to go from a denser medium to rarer medium, you will get an additional phase change of pi. It's like the light gets flipped, and if you get flipped, the phase difference will be pi. For example, if I have a sine wave, if I flip this, it will look like this, right? But it is nothing but if you go back by phi angle, which is basically if you go back by 5, this is how it looks like. So flipping a sine wave is basically going back by 5 degrees. So that's why there is a minus 5. Minus 5 because denser medium to rarer medium, it got reflected. So that would mean an additional phase change of pi. So we have phase difference with additional phase change pi. This has to be a constructive interference. Okay, where is this constructive interference happening? Here. If that has to be a constructive interference, has to be in the sense, if there is any where is the maxima? If I want to find where is the maxima, then I'll have to look for constructive interference. Constructive interference for uh, what is this? Phase difference will be even multiple of pi. So that is what happened here. And this is in terms of path difference. If you remember, in constructive interference, the path difference, this is the optical path difference. That's why there is n here, or else it's just 2D. The extra distance is 2D, but then you have to multiply it with n. If you remember, we saw that it had to be a multiple of lambda. In this case, it is slightly different. Slightly different means the roles got reversed. This is because of this additional pi change. If this pi change hadn't been if it was not there, then you would have found n lambda here and n plus 1 by 2 lambda here. But the roles got exchanged in this case. So careful. Now this is there for constructive interference. This is there for destructive interference. Fine. Newton's rings. That's why for maxima you have this. Now I told you before maxima you'll have path difference will be equal to n lambda, but there was no pi change in that case. Here there is a pi change, an additional pi change. So that's why path difference looks like this and looks like this in the sense odd multiple of lambda by 2. Here you have just a multiple of lambda. Odd multiple of lambda by 2 in the sense you have lambda by 2, 3 lambda by 2, 5 lambda by 2, and so on. Here you'll have, and here you'll now just have, what do you have? 0, lambda, 2 lambda, 3 lambda. So T is the thickness of the, in Newton's ring, if you remember, our thin film is whatever is lying in between this lens and the ground. So ours is a thin film of air. So this is the thickness of the thin film. Thickness changes as you go to the right. That was Newton's ring, if you remember. You'll have many. Fine. I'll just. Okay. What is this? What did this person do? Interferometer, Nobel Prize. So okay. So he made something called interferometer. We'll see what it is. What is happening? Some light rays coming. It's reflected. Okay. Some of it is transmitted. Fine. That gets reflected. That goes down. Okay. Nice. Whatever goes up also goes down. That is also nice. Okay. So some path difference things comes into picture, right? Because some light ray is traveling more. This traveled how much? To L1, again L1. Like, okay, fine. So something, he made something. Fine. And you will surely get some kind of interference because there is a change in path difference. Not change in path, there is path difference. There is change in the path traveled. So there is path difference. Here also you're using this. It means is there any pi change anywhere? Because for destructive interference you'll get this only when there is a a pi change somewhere. Maybe somewhere some pi change is happening. That's why you got this. Oh, now you have a cos theta. Fine. Because, okay, because light is incident at some angle. Previously, no angle, nothing was there, so no cos theta. Everything was normal. Normal incidence. Here there is no normal incidence, so angle matters. So for somewhere angle came. Okay, here also angle is there. Fine. What is happening? The figure parallel rays reaching the eye by reflections from the mirrors appear to come from the external source S behind the eye and mirrors from the virtual sources. Okay, so what is happening? This light went through M1 and it came here. Some of it got reflected, some of it got transmitted and it went there. And this ray is coming, it came here. What about this point? This point went inside. Did it not get transmitted? I mean, did it not get reflected or transmitted? Fine. I wonder what is happening here. Okay, because of these two slabs, I think this person is able to see two sorts of images. Some kind of interference is happening, isn't there? Okay, they are mirrors. They are mirrors. They're not slabs. Fine, they are mirrors. If they are mirrors, then okay, this will go here and this will get reflected. Fine. What is the other thing? There is one more mirror, but how is it affecting us? I don't see how. Fine. Just go on. So sometimes you have a dark fringe. Do we still call them fringes? So minimize sometimes in the center, maximize also sometimes there, and suddenly you have nothing. Why do we have nothing? D. If D is 0, okay, fine. Fine, I mean, this is one formula, it's there for some reason, but it looks like there has been some pi change somewhere, or else it wouldn't look like this. Okay, pi change, I think reflection, right? So from there, I think pi change because of reflection. Fine, you just go diffraction. Fine, okay, interference, diffraction. If there are two sources, then interference. If there are so many multiple sources, then it's diffraction. It's like, yes, sir, this is the story. If you have incident light, then you'll notice there's simply a beam. But if you decrease the B, you decrease this, and if the B is comparable, where is it? Okay, yes, B is comparable to wavelength, then you will start noticing it will like it will, there'll be some interference pattern. So, do we say light is interfering with itself? Something like that. I mean, it's happening here also, but then you won't notice. It's like the effect is small, but it's only observed when you have what is this? When the size of the aperture is comparable to the wavelength of incident light. Okay, they've shown how the pattern looks like. Fine. Okay, airy pattern. This is called airy pattern. So in airy pattern, it's like you have some some sort. Okay, not maybe because some sort of pattern, circular pattern. Joseph Fraunhofer. Okay, we have Fresnel diffraction, Fraunhofer diffraction. Mm, okay, it's basically if this distance is finite, it's Fresnel. If it's like infinite, if light rays are coming from infinity, then that is Fraunhofer diffraction. This is difficult to uh, deal with because since distance is finite, whatever calculations you do, it will depend on d. But in this case, it's coming from infinity, so you won't have this dependence, and it's easier to solve. And how do you produce a light? How do you produce light rays that appear to come from infinity? You just use a lens, right? This will this is how you use them. So they're all when is light coming from infinity? When it's like they're all parallel and they're coming nicely. It's like plane waves. This is coming from infinity. They're all parallel. If you have a point source, and I told about wavefronts, right? So if you are standing, if you stand far away from a point source, so finally it will almost be parallel. So we believe that at infinity they will become straight plane waves. But by that's impractical, right? Why you wouldn't place a light like 100 kilometers away and wait until it becomes almost straight. So you use a lens. That's easier. That's fine. Mm. Yeah. So this is easier to study because Fresnel depends on finite distance, and then in your calculations you'll have to use the distance. It seems like it's one. It is one. Yes, it is one. All of this is fine, and then suddenly this Bessel function got introduced. It's all calculations at this point. In Young's double hole experiment, we got xn right. So similarly, they got their y. Do you have to remember this? I have no idea. Maybe no. Maybe no. But you have to know the concept. So what is the concept? Important conclusion. So yes, so we were talking, right? So if you decrease the size of the aperture, then the effects of diffraction will be more visible. So here, what is A? What is A? Okay, A is the radius of the aperture. Here A is smaller, so greater is the diffraction divergence. Here A is larger. I mean, this looks like diffraction to me than this. But he said diffraction divergence. Okay, let's see. If A increases, Y will also increase. And if A decreases, Y increases. Okay, so since A decreased, Y also, not also, if A decreased, Y increased. So it's like the first ring will be larger. So something like that. That looks like the case. See, here all the rings are small, but here the rings appear to be larger. That means A is decreasing. Nice. So it's like the rings of the pattern are, or the sizes of the rings of the pattern are inversely proportional to the aperture size. So if aperture size increases, then the size of the rings decrease, and you'll be able to notice more rings. That is a different story. Okay, they're defining something called angular spread of diffracted light. So this is there, this is there. So if decreases, if A decreases, then angular spread increases. Yes, kind of. So if A decreases, if the aperture size decreases, then this will kind of increase, I think. If aperture size is too big, then you won't have this effect. The angular dispersion will be less. But if you decrease it, then the angular effects will be more. So that is probably what this is trying to tell. If aperture size is very, very, very small, if aperture size is normal, it's fine. But if you decrease it, then you will get angular effects. So angular spread, fine. So if they ask you what is the angular spread of something, given some aperture size, just you can apply this. This is the radius, not diameter. If you're using diameter, you have to use this. I guess, okay, I think it's one. Nothing much here. About the latest slides, I was not in class, so I might choose not to tell the latest one. So 41, 42, 43. Okay, what is here? Fine, we'll just continue. Spot size. Okay, so I see a spot, so that is spot. it has a size, so spot size, fine. So what is this? Amplitude exponential minus x squared plus y squared by. Okay, so what is this trying to tell me? That is some distribution of amplitude, right? Typically Gaussian. Okay. So here, what is x and y? Maybe fine. If it is moving in z, maybe this is like x and y. Maybe that. Maybe that, yes. So spot size is there and it exponentially decays. So the size keeps decreasing, I think. That is how it's going to look like. Decreasing? No, it should increase, right? What is decreasing? Okay, is the amplitude decreasing? Okay, so amplitude is decreasing, but spot size is increasing. Okay, fine. This is the spot size, right? W is the spot size. This is the amplitude. Light is a transverse wave, so you have transverse amplitude. Amplitude is decreasing in the sense intensity is decreasing. So spot size is increasing, intensity is decreasing. Makes sense because if area increases, intensity will decrease. Area increasing in the sense spot size is increasing, right? Hmm. Okay. So if you have a laser, if you're just shooting light out of it, spot size will increase, intensity will decrease. Fine. Are there any calculations on this? Apart from this, I don't see how do you use that. Okay, so spot size as a function of z. So if z increases, what will happen? This will also increase. So the further you go away, the larger the spot size becomes. Okay, they're giving some condition Fresnel to Fraunhofer. When does Fresnel become Fraunhofer? When light, when z is very large, right? So this seems to be a large number, maybe. In that case, what will happen? Okay, in that case, this one will become insignificant. Fine. In that case, one will become insignificant. Then square root will come. Fine. Laser beam width increases linearly. Okay, fine. So initially it will look like this, but slowly, like at farther distances, it will appear as though the increase in width size is linear. So fine. Tan theta. Tan theta is what? This is the width size. Width size. What is that? Width size. Width size. Yes. Beam size. Whatever. And this is the z. So approximately tan theta is approximately width by z. So that is what they wrote here. This is true for large z because linearity is almost achieved when z is large. Fine, so some calculation we got here. So maybe you could keep this probably, or maybe this. This is an approximation. This is only when z is large this is happening. I don't see anything else here. So the spot size, yes, spot size increases and intensity decreases. That is fine. Why is intensity decreasing? Because amplitude is decreasing. It's like the energy is getting spread, so that's why intensity decreases, doesn't it? So what used to be a nice little spot, nice little dark spot, spot size increases and it has the energy has to be split, right? So when spot size becomes too large, the light is too faint, so you won't be able to detect. This happens when you go farther and farther away. Fine. So I was telling 41, 42, 43. I don't think I will be doing because I was not in class, I think. Maybe you could just go through these yourself. But leaving behind 41, 42, 43, if we leave this part, I think I've covered everything after minor 2. About the portion before minor 2, we'll see. If there's any free time, then we'll look into it. So now I'll stop the live stream. Live stream, live stream, live stream.